day everyone! In this video, we're going to tackle about the polarity of molecules. A. Polarity of bands and electronic negativity. Electronegativity, or EN, measures the relative tendency of an atom to attract electrons to itself when chemically combined with other atoms. Take a look at the electronegativity values of some electrons in Figure 1. What have you noticed? Correct! It increases within period from left to right and decreases within a group from top to bottom. So what is the connection of the electronegativity to the polarity of bands? We could use the electronegativity values of the atoms involved with the absolute electronegativity difference, which will help us in predicting what type of chemical band are a unique polar covalent or non-polar covalent that would exist between them. Table 1 shows the type of band based on electronegativity difference of banded atoms.
Table 1. Type of band based on electronegativity difference of banded atoms. So, here's of type of band and electronegativity difference. First, ionic. Electronegativity of difference is greater than or less than 1.7. And polar covalent 0.5 to 1.6. Non-polar covalent less than or equal 0.4. For example, number 1, calcium and chlorine. The En of calcium is 1.0 and En of chlorine is 3.0. So 1.0 minus 3.0 is equal to 2.0. It's ionic band. Number 2, chlorine and chlorine. The En of chlorine is 3.0. So 3.0 minus 3.0 is equal 0. It is a non-polar covalent band. Number 3, hydrogen and chlorine. The En of a hydrogen is 2.1 and the En of chlorine is 3.0. So 2.1 minus 3.0 is equal 0.9. It is a polar covalent band.
Using the above examples, let us know more about polar and non-polar covalent band. A polar covalent band is formed when electrons are shared unequally by two atoms. Is a compound, the bonded pair of atoms for an electron dipole. Dipole means two poles, which means that a molecule has one positive end and one negative end. In this type of band, the atom with the higher En value becomes the partial negative pole, while the atom with the lower En value becomes the partially positive pole. Always bear in mind that the direction of the arrow is always pointing from more electropositive pole to the more electronegative pole. HCl or hydrogen chlorine, for example, each has higher En than Cl. Thus, the direction of the arrow is from each pointing to Cl, and there is unequal electron density as presented by the size of the circle. On the other hand, a non-polar covalent band developed in both atoms equally share a pair of electrons between them.
B. Polarity of molecules and molecular geometry. You can predict the shape of molecular geometry of a substance using the following steps. So, step 1, determine the central atom of a molecule. The central atom is the less electronegativity element. Step 2, draw the appropriate Lewis dot structures for the molecule. Step 3, count the number of bonding pairs of electrons and non-bonding or lone pairs around the central atom. Step 4, determine the electron pair orientation using the total number of electron pairs. Step 5, name the shape based on the location of the atoms.
As shown in Figure 3, different molecular shapes. Consider the examples below. Example 1, predict the molecular geometry of BCl3. Step 1, EnB equals 2.0, EnCl equals 3.0, therefore, B will be the central atom at the three Cl atoms are attached to it. By looking at the chemical formula, You will also have an idea that boron will be the central atom and 3 atoms of fluorine are attached to it. Step 2, you can see the bonding pairs of electrons. Step 3, the central atom has 3 electron pairs. 3 bonded pairs are no lone pair. Step 4, the electron pair orientation for 3 electrons is trigonal planar. Step 5, the molecular shape of BCl3 is trigonal planar. Example 2, predict the molecular geometry of CO2. Step 1, ENC equals 2.5, ENO equals 3.0. Therefore, C will be the central atom and 2O atoms will be attached to it. You may also use the chemical formula to predict which atom will be the central atom. Step 2, you can see the carbon dioxide are separated into each other and atoms are attached to it. Step 3, to determine the position of the bonding pairs, let us count the double bonds as one bonding pair. Therefore, CO2 has 2 bonding pairs of electrons. Step 4, the electron pair orientation for 2 electron pairs is linear. Step 5, the molecular shape of CO2 is linear. Example 3, predict the molecular geometry of CHCl3. Step 1, ENC equals 2.5, ENH equals 2.1, and ENCl equals 3.0. Because carbon is less electronegativity than chlorine and hydrogen is normally terminal atom, C must be the central atom. Step 2, you can see the hydrogen, carbon, and chlorine. Step 3, there are 4 bonding electron pairs. Step 4, the electron pair orientation for 4 electron pairs is tetrahedral. Step 5, the molecular shape of CHCl3 is linear. Now that you have learned how to determine the molecular geometry, let us now go on to our discussion of the polarity of molecules based on molecular shapes. You may study the diagram below and we will use it as our guide.
Is the shape symmetrical in 3D? If no, the molecule is polar. If yes, are all atoms bonded to the central atoms the same? If yes, the molecule is nonpolar. Take note that you must think about a molecule in 3D according to VSEPR theory.
Now, let us see if you fully understood our discussion. I want you to try answering the exercises below. Identify which molecule is polar and which is nonpolar given the Lewis structures and molecular shapes of the following molecules. If you were able to answer that NH3 and H2O are polar molecules because the bond depot cannot be cancelled because of the presence of lone pairs on the central atom, and CCl4 and HBr are nonpolar molecules. You are correct! Job well done!
You must also take note that in a symmetrical molecule, the sum of bond dipole is equal to 0 because they cancel out, which leads to the formation of nonpolar molecule. Therefore, both BCl3 and CO2 are nonpolar. That's all! Thank you for watching!